The Tesla factory, America's largest industrial plant.
Behind me is one of the largest hydraulic stamping presses in North America. It's actually 7 stories high.
For this cutting-edge facility to build electric cars,
Suddenly, science fiction isn't tomorrow, it is today.
engineers had to look to the past
This beautiful machine, it's one of the world's first electric cars. Brilliant engineering.
to make the impossible possible. Since the Industrial Revolution, factories have often been portrayed as dirty and dangerous places, churning out products at the expense of the workforce. But one American factory is challenging this view. The Tesla factory. Located in Fremont, California, this state-of-the-art automotive manufacturing facility is kickstarting a new technological era. And Tesla's Alexis Georgeson has witnessed the birth of this giant industrial machine.
The processes here in this factory are designed to be efficient as possible. It's a 5.3 million square foot facility.
This American car manufacturer revolutionized the industry with the world's first electric sports car. But producing hundreds of thousands of electric cars for mass consumption required an even greater scale of engineering.
That's one of the biggest challenges ahead, as our CEO Elon Musk has said, is really building the machine that makes the machine.
Starting production in 2012, this machine is the biggest factory in the Western Hemisphere. The 5.3 million square foot factory employs 6,000 workers and state-of-the-art robots to transform raw materials into high-tech vehicles in just a few days. Here, the staff and some of the world's mightiest machines come together to cast, stamp, paint, and assemble component parts into 2,000 cars every week. That's before they go through the final lap on the factory's dedicated test track. But making this many cars in a factory this big would have been impossible without mass production.
We're rethinking the way that the automotive industry has approached production in the past through first principles of physics and through vertical integration, and just really treating this as an engineering problem first and foremost.
Once upon a time, there was no such thing as mass production.
Sword, please.
Everything was made by artisans.
Thanks, peasant.
Though charming and unique, the process was inconsistent,
What a chopper!
Mine's a tiddler.
expensive,
More. More. More.
and slow. With this approach, making mass quantities of products was impossible.
What's this? Grrr.
But a revolutionary change was on the horizon. Architect and historian Benedetto Camerana is in the iconic city of Venice, Italy, to reveal where mass production got its start.
In the Middle Ages, the Republic of Venice was a political power with a strong reputation for war and conquest.
The strength of the Venetian Empire was based on naval muscle and commercial trade. Both needed ships, and lots of them.
Naval boat building had been carried out in different shipyards, sprawled throughout the city. That it would take weeks to produce a single galley, and that was not fast enough.
In the 12th century, the Venetians developed a game-changing solution.
And this is it, the Venice Arsenale. Here, they completely reimagine the way that ships were built.
For the first time in history, each individual component of a ship was mass-produced across a centralized row of specialized workshops.
The ships were moved around the dockyard to different workshops, each focused on prefabricating the different elements of the ship.
Hulls were made and launched as shells. They were then towed across the shipyard and equipped with ready-made masts, rudders, and anchors. At the final workshop, they were rigged and set up with oars and armaments.
At its height, they could assemble a galley per day here, which is truly incredible.
At the Arsenale, Venetian shipbuilders invented the production line. In bringing this production line into the 20th century, engineer Giacomo Mattetrucco designed another one-of-a-kind factory in Turin, Italy, for the car company Fiat, called the Legato.
When it was completed in 1923, this was the largest car factory in the world, 5 stories high.
For the first time, all aspects of production came together in a single building. Specialized workshops were placed strategically on each floor, producing parts that would be fitted to the vehicles as they progressed through the 1,600-foot-long factory.
Raw materials would arrive by rail to the ground floor of the building. Here, they would be fashioned into car components. On the second floor, the engines and bodies of the car were made. 1 story up, gearboxes and steering were added. The 4th floor specialized in brakes and upholstery. And on the 5th floor, finishing touches were made. Finally, the completed cars would emerge on the roof, the most iconic feature of the building.
All the cars coming off the Legato production line came here, a purpose-built rooftop test track.
For nearly 60 years, this phenomenal test track, high above the Turin skyline, would have been witness to the birth of hundreds of thousands of cars.
For over 50 years, the Legato factory produced countless vehicles until 1979. But its tremendous legacy lives on. At the Tesla factory in Fremont, California, the principles of mass production first applied at the Venice Arsenale and further developed at the Legato are getting a 21st century makeover.
We move cars from one end to another. So much of the factory is vertically integrated. We're actually producing so many components here in-house rather than shipping them from other parts of the world or other parts of the country.
While the production line principles remain the same, compared to factories of the past, the Tesla factory is practically unrecognizable.
We wanted this first and foremost to be a beautiful working environment that really was a testament to the quality of the products that we were building here. So we came in, we repainted the entire space, we put sunlights in the roof, we wanted a lot of natural light and a place where workers could come and be proud of the craftsmanship and the space where they were creating these products.
But to create a truly futuristic factory filled with cutting-edge robots, the engineers had to draw on the great innovations of the past.
The robot is correcting itself to achieve its objective.
To deliver more impossible engineering. The Tesla factory. As the largest industrial plant in America, this cutting-edge electric car company has one of the most advanced production lines on the planet. The 5.3 million square foot factory takes raw materials in at one end and, in as little as 3 days, transforms them into cars. 6,000 workers interact with the most futuristic technologies to produce a staggering 2,000 electric cars a week, all of which go through the final lap on the dedicated test track. But to produce vehicles on this vast and ever-growing scale, engineers had to design with extreme economy.
How do we streamline this? How do we ramp production? How do we keep the cost down? And how do we make this manufacturing process as efficient as possible?
To be ultra-efficient, the engineers looked to one of modern history's great breakthroughs: robots. Science communicator Kate Mulcahy is in southwest England to find out how a scientific investigation into brain function actually led to a breakthrough in robotics.
Oh, Lord alive. As I attempt to cross this beam, signals are being sent to my brain through my eyes, my inner ears, and my sensory systems. This feedback helps me to correct my weight distribution, and hopefully I won't fall.
Each time Kate feels herself losing her balance, her senses warn her. This sensation is something that scientists call negative feedback.
Yes!
For decades, scientists tried to incorporate this negative feedback into robots so that they could direct themselves. And in 1948, American-born neuroscientist William Gray Walter had a breakthrough and invented a truly pioneering robot.
And here it is. Each machine contains 2 valves, 2 relays, 2 motors, and 2 sensors, one for light and one for movement. So essentially, it's a 2-cell nervous system, which when you think about it, compared to the billions of nerve cells that are in our brain, isn't that many, but it still did something really amazing.
Gray Walter called his device the tortoise.
The tortoises are designed to sense the light and move towards it. So, you can see it heading towards the light bulb right now.
The tortoise uses a photoelectric cell to detect the light.
That's the sensor you can see on top of it moving back and forth. When it registers the light, it stops the steering and moves towards it.
Because there are different light sources in the room, the tortoise regularly stops to check its position before adjusting its direction to move closer to the brightest light.
So that's negative feedback. Just like when I was balancing on the beam and adjusting myself, the robot is correcting itself to achieve its objective. Now, if we put obstacles in its way, things get really interesting.
The shell of the robot now acts as a bump sensor.
So it's making decisions based on 2 sensors. One is sensing the light, and the other is detecting the obstacles.
Though it may look simple, this is actually complex behavior. The tortoise has a different solution every time the experiment is run, and each path it takes involves a multitude of different corrections and movements.
Every reaction they make is a result of sensing the environment around them. Then they react and create a new path. Amazing.
For the first time, a machine could demonstrate a complex decision-making process, and this discovery paved the way for a revolution in robotics.
Autonomous machines have come to replace humans in many realms, from the domestic to outer space, and they've revolutionized the industrial world.
But at the Tesla factory in California, engineers are integrating robots and workers to a much greater degree than the factories of the past, making it one of the most automated facilities on Earth. Some robots here even resemble Gray Walter's breakthrough tortoises.
We've solved a tough logistics problem in the factory too with the use of robots. So our cars actually move around several sections of the process of production on these little smart carts. They're robots that actually follow these magnetic strips in the floor, and they move from one section to the next following these little strips.
Also using negative feedback, these robotic vehicles use sensors to spot people or objects in their way and wait until the path is clear. Incredibly, they take themselves out of rotation when their batteries run low and put themselves back when fully recharged. And the simple guidance system allows their routes to be adapted instantly. But these carts are relatively primitive compared with most of the factory's robots.
The robots behind me are KUKA robots. They're actually trained to do up to 5 tasks. They rivet, they weld, they glue, they move pieces from one part of the line to the other. So they're incredibly smart robots.
Hundreds of the KUKA robots perform amazingly complex but repetitive tasks with incredible precision and without ever getting bored. But when it comes to heavy lifting and carrying 5,000-pound cars dynamically, engineers at the Tesla factory had to develop even more serious heavyweights.
So most conventional robotic arms that you'd find in the market wouldn't be able to lift weights nearly as close to this one.
To make the impossible possible. The Tesla factory. As the largest industrial plant in the Western Hemisphere, this technologically advanced facility uses cutting-edge robots to help produce an astonishing 2,000 electric cars every week. But for robots to actually lift and rotate 5,000-pound cars, engineers had to rely on a breakthrough innovation.
This is one seriously impressive robot. This is the Fanuc M2000 IA1200 multi-arm manipulator. Now, this robot is so strong, it's capable of doing 4 times the work of a conventional robot. It's able to lift a really impressive 1.2 tons, and it's used on the Tesla assembly line. But its bigger brother, which is also in use on the Tesla assembly line, can lift a huge 2.3 tons. Now, that's really useful if you want to move a car in a single lift. So most conventional robotic arms that you'd find in the market wouldn't be able to lift weights nearly as close to this one. On top of that, this robot is capable of running 24 hours a day and 7 days a week. Yes, it's working. Traditional ways of moving heavy weights, such as lifts or hoists, can only go up and down, whereas this, because of its 6 different axes, allow this robot to move with unbelievable accuracy. It's exactly this that Tesla uses to save them both time and money, and to ensure that cars can keep rolling off their production line. And all of that make this a truly incredible feat of robotic engineering.
Twelve of these heavyweight robotic arms use the 6 different axes to provide both flexibility and sheer power to keep the car production going. Named after superheroes, the likes of Wolverine and Iceman continually lift up these heavy cars without breaking a sweat.
Robots are incredibly valuable in the automation of this process and helping us to ramp production and to make this process as seamless as possible.
But robots aren't the only remarkable machines required for a 21st century car factory. To produce hundreds of thousands of electric cars, Tesla's engineers must continually satisfy a very modern challenge.
All of this is an effort to build as many electric vehicles and get them on the roads as quick and seamless as possible.
The state-of-the-art Tesla factory is capable of producing electric cars in the kind of quantities once reserved for vehicles that use gasoline. But to produce electric cars quickly, efficiently, and economically, engineers had to invent a completely new way of building them.
The way that other manufacturers have built electric vehicles in the past was to basically gut internal combustion engine vehicles and put battery packs wherever they would fit. But we built the car from the ground up.
And this new process starts with the basics.
Behind me are giant coils of aluminum. This is the start of production for these vehicles. It's the raw material that comes through this end of the factory. There are 20,000 pounds of aluminum coils.
Traditionally, most automobiles are made with steel. But because the batteries that power electric motors are so heavy, manufacturers had to use a different material. Aluminum, which is more commonly used in the aerospace industry.
Aluminum is incredibly lightweight, very durable, and safe. We've really designed these cars from the ground up to maximize safety and efficiency, and aluminum helps us do that.
But how can you turn aluminum sheets into car body parts quickly and accurately enough and still make production cost-effective? To do this, engineers had to look to another manufacturing breakthrough from the past.
And his methods were picked up and used by Henry Ford and other pioneers of the automotive industry.
To make the impossible possible. The Tesla factory in Fremont, California, is the largest industrial plant in the Western Hemisphere. This futuristic facility produces over 2,000 electric cars every week, made of aluminum. But to shape the vehicles with this material, engineers had to rely on an inventive manufacturing process from the past, the industrial press. Today, bicycles are everywhere, but when they first appeared, they were strictly for the rich. Historian Chris Sweet is on the trail of the industrial innovation that brought bicycles to everyone.
Late 19th century bikes were luxury items, costing up to $100 each. That was as much as an average worker would make in 6 months. But all that changed here in Chicago.
In the late 19th century, entrepreneur Adolf Schoninger revolutionized how bicycles were made. Because early metal bicycles were manufactured using a cumbersome process, Schoninger hoped to improve the building technique.
The traditional method of making bicycle components was known as drop forging. It involved taking a chunk of metal and heating it till it was malleable, like this chunk of clay, and forging it into shape by repeated pounding. It was a long, labor-intensive, and expensive process. That is what Schoninger wanted to change. And this is what he did. He came up with an industrial press to shape cold steel. Imagine this sandwich maker is our press. We put in this sheet of cold steel, press it. Out comes a three-dimensional bicycle component ready to be assembled and painted.
By pressing bicycle components with an industrial press instead of forging them, Schoninger slashed the prices of its bicycles, finally making them affordable to the general public. Soon, Schoninger's Western Wheel Works was turning out 70,000 bikes a year, with markets as far away as Europe, transforming Chicago into the bike capital of the world.
And his methods were picked up and used by Henry Ford and other pioneers of the automotive industry. The mass stamping of parts revolutionized manufacturing in America and around the world.
At the Tesla factory, engineers have supersized Schoninger's revolutionary industrial press to shape the cars.
This is one of the largest hydraulic stamping presses in North America. It's actually 7 stories high. We can only see 4 stories. 3 of them are actually underground. There are 5 main sections of this press, each one weighing up to about 1 million pounds.
The giant stamping press uses a variety of heads to turn the flat sheets of aluminum into all kinds of ultra-lightweight car body parts. And cold forming the aluminum helps preserve the physical strength of each component.
You need a machine that can exert a ton of pressure and force down on those panels without a lot of heat. That's what this hydraulic press is capable of doing. We take those sheets of aluminum that you saw, and they're actually stamped between 4 to 5 times as they move down here.
This powerful press is capable of exerting around 9,000 tons of pressure per square inch, the equivalent of having 3,000 cars pressing down on your thumbnail. The 7-story tall monster press can create strong, complex shapes quickly and at a much lower cost than other techniques like hot forming or machining.
This is an incredibly important machine to us to help stamp the individual parts for Model S and Model X. They're electric vehicles, and they're already very heavy cars because battery packs weigh a lot. So it was important that the other parts of the vehicle be as lightweight as possible for efficiency. The aluminum panels make the range and the safety very, very possible in these cars.
But these fresh pressed panels must also be painted. So, how do you efficiently paint 2,000 cars a week without waste? This would have been impossible without the innovation of electrostatic painting. To reveal the origins of industrial painting, physicist Susie Sheehy is visiting an inner-city graffiti workshop where the inefficient use of paint is clear.
Spray painting is a brilliant way to cover a surface area with an even coat of paint. But as any graffiti artist can tell you, it's pretty messy and inexact. As the paint particles are released from the pressurized canister, they have a tendency to go everywhere, all over your hands and the floor. And that leads to a lot of wasted and scattered paint, which is both costly and inefficient.
During the Depression of the 1930s, Harold Ransburg was working at his father's houseware factory when he saw how much industrial paint was simply getting wasted.
This salt shaker is exactly the kind of article that Ransburg was trying to paint. So if I try and paint it, you can see there's a lot of mess and a lot of wastage, and I haven't even really achieved a very good finish. You can imagine on an industrial scale how expensive that would be.
So, with lab assistant Harry Green, Ransburg experimented with electrical currents. Because negative and positive charges attract each other, Ransburg and Green introduced an electrical charge to the painting line in order to attract all the paint to the product without waste. And in 1938, Ransburg spent all the money he had, $35, to buy a high-voltage transformer typically used in hospital X-ray machines.
I'm going to use a Van de Graaff generator instead, but the principle is more or less the same.
This generator uses a moving belt to build up an electrical charge in a hollow metal globe.
So if I connect this up, that will give a positive charge to the shaker, and then the paint, which is still neutral, is going to become attracted to it. At least that's the theory. All right, so if I just ground the paint tin, switch it on. Let's see. Oh, that's great. So it's actually coating all around the sides. It's actually pulling the paint all around onto the back. It's got a really good coverage, and actually there's a lot less paint wasted as well.
Called electrostatic painting, Randsburg's pioneering technique transformed industrial painting across the world.
You might not realize it, but electrostatic painting is used to decorate all kinds of everyday objects, from shop fronts to railings, lampposts to bicycles. We are surrounded by the fruits of Harold Randsburg's innovative approach to painting.
"80 years on, the Tesla factory has taken electrostatic painting to a level that Harold Randsburg could only have dreamed of. In a state-of-the-art paint shop, each car is attached to an electricity source and grounded. Robots spray positively charged paint that is electrostatically attracted to the car. Primer, color, and finally a clear coat are efficiently applied with very little waste to create a completely flawless finish. But mass-producing electric cars effectively and efficiently isn't the only challenge the factory faces. To surpass the high expectations of the car-driving public, Tesla's engineers had to overcome the historic problems of the electric car.
20 miles an hour. I'd say that's about as fast as I'd like to go.
To create even more impossible engineering. In California, Tesla's engineering innovators are in the process of creating the factory of the future, attempting to turn the more than century-old automobile industry on its head. They're using advanced robotics and technology to bring back the electric car and transform it from a niche item to an everyday, mass-produced product. Everything about the 5.3 million square foot facility is designed for speed, accuracy, and efficiency. But technical advances aren't the only challenges the factory faces. It must also turn out a vehicle that the public, who are used to the speeds and distances that internal combustion engines provide, will actually want. In 1908, Henry Ford had a bright idea. To bring the internal combustion engine to the people. The revolutionary technology changed the world. Demand for gasoline went through the roof.
I'm rich.
Cities swelled as new suburbs within reach of the workplace grew.
Hi, honey, I'm home.
Modern life quickly centered around the internal combustion engine. And people could go faster and further than ever before. But once upon a time, the combustion engine had a surprising rival, the electric car.
This is a Pope Waverley. Built in 1901, it's one of the world's first electric cars. And this particular one was used by Harrods for deliveries.
Physicist Susie Sheehy is taking a ride on this classic piece of American engineering.
And it's a little known fact that at the turn of the century, about a third of all cars were electric powered.
When the automobile was first invented, there were three main forms of propulsion: internal combustion, steam-driven, and the popular battery-powered engines.
Now, this beautiful machine, in its day, would have had a range of about 20 miles and a top speed of a whopping 20 miles an hour. But having driven in it for a while, I'd say that's about as fast as I'd like to go.
But electric cars were soon eclipsed. because automobiles running on gasoline developed a longer range, became more reliable, and got much faster, leaving the electric car in the dust. But Tesla's designers and engineers believe they've overcome the problems that held the electric car back. To see how, rally race driver Alex Roy is taking the Model S out for a test drive.
Earlier generations of electric vehicles didn't have the benefit of batteries with decent power density. It is the first time that you have an electric vehicle that's a genuine sports car. The Model S, you can do this. And that is Ferrari level acceleration. It's impressive.
The beating heart of the design is the powerful electric motor. And it couldn't be more different from a traditional internal combustion engine. The standard gasoline engine has hundreds of moving parts. But the motor on the Model S and Model X only has one moving piece, the rotor. Powering it are nearly 7,000 small lithium-ion batteries packed into a tray that fits in the floor of the vehicle. And to produce these batteries, Tesla is doing something extraordinary. Creating an even bigger factory, the size of which has never been seen before on planet Earth.
It's still under construction. We're building it in phases so that we can actually start production of batteries, cells, and packs inside while we continue construction outside. That factory will, once complete, be the largest building in the world by footprint.
Called the Gigafactory, this enormous solar-powered facility in Nevada will take the mass production of batteries for electric cars to an unprecedented scale.
Within a couple of years, we'll be putting hundreds of thousands of battery packs out every year.
These powerful batteries, combined with radical automotive design, allow the electric car to drive much further distances. But to compete with the hundreds of miles that gasoline-powered vehicles can go on a single tank of gas, Tesla's engineers had to give the electric car yet another source of power.
It's an absolutely brilliant piece of engineering. And suddenly, science fiction isn't tomorrow, it is today.
To make the impossible electric car possible. The Tesla factory. As the largest industrial plant in America, this facility has produced and sold over 200,000 electric cars worldwide. But making a battery-powered vehicle that can drive as far and as fast as gas-powered cars would have been impossible without giving it more power. Anyone who's ever ridden a bicycle knows how much power is wasted when you brake. The kinetic energy from the bike's forward motion is thrown away as the brake pads rub against the tires, converting that energy to heat. Just how much energy is lost becomes painfully obvious when you start pedaling again. Determined to use the energy normally lost in braking, Tesla's engineers have coordinated the motor to work with the brakes. When the brakes slow the vehicle, the motor also acts as a generator and converts the otherwise wasted energy into electricity, returning it to the batteries. This energy recycling process is called regenerative braking.
Regenerative braking is a technology that grew out of racing. And in Formula One, regenerative braking was developed to make cars go faster. In a Tesla, that extends the car's range, and is one of the reasons the Tesla has a range of 300 miles as opposed to earlier generation electric cars, which are restricted to 250, 200, even 150.
All this means electric cars can now match the distances of gasoline-powered vehicles.
If you didn't have a regenerative braking system dumping power back into the battery, I would imagine you'd have somewhere between a 10 and 30% drop in range. It's an absolutely brilliant piece of engineering. And suddenly, science fiction isn't tomorrow, it is today.
These trailblazing engineering innovations would not be possible without the giant cutting-edge factory that builds them. This extraordinary engineering process begins with humble coils of aluminum sheets and ends just a few days later on the test track.
That can-do think outside the box is really something that informs both the vehicle and the factory side of the equation here at Tesla. You'll see that both in the engineering of our products as well as the engineering and in our approach to manufacturing and production within this facility.
By drawing from the great innovators of the past,
This was the largest car factory in the world.
Oh, that's great.
Amazing.
adapting their ideas and making trailblazing discoveries of their own.
Every single manufacturer will be making a car just like this with their own brand on it within 5 years. Things can be done better. You don't have to be trapped in the past.
The planners, designers, and engineers behind this futuristic factory are succeeding in making the impossible possible.
Being in this factory certainly is something that I think every employee can agree is something they're incredibly proud of.